Now that we have our coordinated turn and our trim trajectories, we're now going to start developing linear models for our system. And the first approach we're going to take is we're going to call this transfer function models. And it's really kind of a fun approach. What we're going to do is we're going to just treat small things as disturbances and try to produce linear relationships. So where the linear component dominates, we'll be able to just eliminate all the nonlinear stuff that's quote unquote small under nominal conditions. And then at the end, we'll actually have to do a linearization about the nominal trajectory for part of our transfer function. This will be used in Chapter 6 for successive loop closure. We're going to develop a whole bunch of transfer functions, and then we're going to develop control laws, largely proportional derivative and integral control laws to use these transfer functions to control the system. So let's go ahead and get started. The first thing I want to pull up is, or just remind you of, is the Laplace domain. So we have a nice relationship where the time derivative of x becomes, we'll just multiply this times, if we take the Laplace transform of it, it's going to be s times capital X of s. And if we take an integral of x, that's just going to be 1 over s x of s. So the frequency domain, or sorry, I should say the Laplace domain, is really nice for integration and taking derivatives. So we're going to be developing models for lateral motion acting in the horizontal plane. So in this case, that's if we looked at the inertial frame, that's just in the northeast plane. Right, so this is horizontal. This is going to be talking about our roll rate, heading, yaw rate, and our lateral velocities. For controls, we're going to use our ailerons and rudder for the lateral motion. So if we were to grab or take a look at our aircraft, right, the ailerons and rudder is going to be what causes it to do that side-to-side motion. And what we're going to do is we're going to control our course angle and our side slip. And in reality, I'm going to cross off heading and yaw rate. We could use those, but for the transfer function models, we're actually going to just replace these with our course angles, our course angle and our side slip. Okay, so because that's what we're going to end up controlling. In the longitudinal section, when we're developing models for the longitudinal motion, and the vertical should be plane, the states we'll care about are our pitch rate, altitude, airspeed, and the inputs will be our elevator and our throttle. And we're going to control our altitude and our airspeed. So we'll jump in and start looking at our lateral motion. Okay, so when we look here's our equations of motion. And one thing to notice here is that we are missing the effect of our throttle. So we have Q sub P delta T VA. This will be minus gamma 4 QP delta T VA. I just want to bring that up in case you notice that in your reading. Right, so the variables that I mentioned for our lateral motion is we were going to use our yaw angle. We'll use, and I should have highlighted our roll angle, right? Then we have our roll rate and our yaw rate. These are all lateral motion variables. And we'll use also our velocity out the wing, right? So our side-to-side velocity. And in reality, we're actually not going to use yaw because we'll develop our control for our course angle And we'll use our coordinated roll motion for that. One thing you'll notice here is that we're going to, oh, and I mentioned that we're going to use our delta A, and we're going to use our delta R, delta R over here, for our control inputs. So the first model we're going to look at is we're going to look at how delta A affects, obviously, P, and then P has a large effect on phi. So that's our first model. So we have delta A affects P, our roll rate, and which then affects our roll angle. So we're going to look at that relationship right now. Okay. So let's try to see if we can, so we have that. Let's see if we can find this a transfer function that will relate our motion, or our desired, our input for our aileron to our roll angle. Okay, so we're going to just start off with phi dot, and we take phi dot directly from the equations that we had above. And we'll look at these angles, and assuming that theta is small, right? If theta is small, then the tangent of theta is small. Okay? So in this case, we're going to say that that kind of removes some of those terms, or at least we can chalk those terms up to being small. And so we define first our first disturbance. So we're just going to take all of this stuff right here, and we're going to throw it into this thing that we call our disturbance. And that's what we're going to be doing in this transfer function section. And so all we're doing is trying to figure out or look at the equation, say, that's actually kind of small, so we can ignore it. So if we do that, then the time derivative of our roll angle is equal to the roll rate plus some disturbance. Okay. So now if we take the second derivative of this guy, because what we want to do is find the relationship to our delta A. So find the relationship to our input. So since it's not in this equation yet, we're going to differentiate. So we're going to differentiate, and we're going to take this value of P, we'll get P dot, and we see we have P dot defined above, and so all of this is just coming from P dot. Okay, so we're going to then take it, and we come in and we just start organizing like terms. So we have, and we start substituting some things in. So for example, we have P right here. Well, we said that P is approximately equal to phi dot minus our disturbance. So that's where we get that term. And everything else basically stays the same. So then we group things. This allows us to have a phi dot term in there. And so we group everything with a phi dot out in front of it. So here we have that term, right? We group everything with our aileron, because we know that our aileron is going to be affecting our roll angle. So in essence, we get this term, right? And then everything else we chalk up to a disturbance. Now, there's some reasons for those being chalked up to disturbance. These coefficients are somewhat small and things like that. So, and it goes into a little bit more detail in the book. But at the end is we have constants. Can't spell. We have constants for multiplying in front of our phi dot and our delta A, and then we have some disturbance that we'll just ignore for now. Excellent. So that then helps us get into our transfer function. So we'll only do this once. So this is our phi dot, but I do want to do it once to help you understand how we're jumping into our dynamic equations, right? So this guy, we would have an s squared times phi of s is equal to, we have this minus a phi 1 times s phi of s. So as we convert down here, we're doing the Laplace transform, right? Plus a phi 2 delta a of s plus, and then we'll just chalk this up to our disturbance in the Laplace domain. Okay, now to get to this model, all we're going to do is we're going to bring all of the phis to one side. So we'll have phi of s times, we're going to have s squared, and we have a plus a phi 1 times s is equal to a phi 2 delta a of s plus that guy right here. So now we see that this ends up popping up on the bottom. And we can factor out an s out of here, just like we did here on the bottom. So that's how we get that transfer function model. Once we've defined something in terms of just these constant coefficients, we can use those simple properties of the Laplace transform when we're taking derivatives and integrals, and immediately arrange terms and get phi all by itself, or whatever variable we're looking at. So we now have this transfer function. We went from our second derivative to this transfer function model. So then we can write it up in a block diagram form, where we have phi of s as the output, and we have our delta a, so our aileron is our input. And this guy is just a disturbance. Okay. One thing to note is that we have this extra integrator here. So this is a 1 over s. This is an extra integrator. So we could write this as we have delta A and our disturbance coming in. I'll just write it like that. Going into the equation, we'll have a phi 2 all over s plus a phi 1. And this is almost p, right? We talked about that there should be one more disturbance, but the book doesn't end up quite showing that. And then if we integrate, then we'll get phi of s. So we can separate this block diagram, noticing that there's an integrator and that p is almost the derivative of phi. We can write our transfer function as such. Okay. And so that's what we get. That's where we got this component of our transfer function. Excellent. Now we want to get to our course angle. Again, our delta A, we want to see how that affects our course angle. We have this nice relationship that the time derivative of our course angle is taken from the coordinated turn. So we have the time derivative of our course angle in terms of a very nonlinear function of phi, but we'll notice that tangent is somewhat close to being equal to phi around phi equal to 0. So what we're going to do here, we're going to add and subtract. So we'll just say that this is equal to plus g over vg phi minus g over vg phi. So we can always add 0. And then we group terms, and we can say that our tangent of phi is nearly equal to 0. So this guy is almost, this is really small. So when we group those like terms, then our course angle is related. We have a V over G, or a G over VG times phi. So that's the main component. And then we'll chalk up this guy to some disturbance. And so that's what we have coming in here. We have d sub our course angle coming in, and we get our course angle out. So we have phi coming in, we have our disturbance coming in, and we get our course angle out, which is great because now we have our aileron as the input, and we have a nice relationship all the way out to our course angle, which is one of the things that we're trying to control. Okay, the second thing we're going to look at in our lateral functions is our side slip. So we're going to try to control our side slip, try to keep our side slip equal to 0, because that's really where our dynamics are closest to being linear, is right if our side slip is equal to 0. So if we were to look at equation 2.7 in the book, that gives us that VR is equal to VA sine of beta. Okay. Now, if we have no wind, then we have that V is equal to VR. So that's where we get this relationship here. So we have no wind condition, V is equal to VA sine of beta. And if we have a constant airspeed, now if you remember those simulations from before, our airspeed actually stayed fairly constant if we were at trim. So if we have our constant airspeed, all that does is say that when we say that this should have a plus V dot times VA dot sine of beta, but we're saying that that guy is equal to 0. So then we have this relationship that V dot is equal to VA cosine of beta times beta dot. V dot is just equal to this big thing right here. So now we have VA cosine of beta times beta dot is equal to V dot. We're going to then solve for beta dot, and we'll group terms. And if we do so, we have a term right here that's multiplied by beta. We have a term right here that's multiplied by delta R, and everything else, right, all the stuff that I'm underlining, we chalk up to disturbances. Okay, so we'll just say that's a big disturbance, and these things are really close to 0, especially around our nominal trajectory. Now, we really want these to be constants. And we'll say that if we're driving beta to 0 and trying to keep beta at 0, then the cosine of beta is really close to being 1. So we can get rid of the cosine of beta in those two functions. And then we have our constants. So we're just, again, looking at things, seeing what things look small, and we'll just chalk those things up to disturbances, and we'll take the rest. Okay, then when we come into it, we have our Sideslip Dynamics. This is just the equation that we were just looking at. And we can write it up into a nice block form, again, taking the Laplace transform, and we have something where we have our input is our rudder, and our output is beta. Right, so we have this nice, just a nice transfer function relationship. Okay, and you'll see here that we've gotten rid of that cosine term. Okay, so we have our side slip dynamics. So now let's we're going to jump into our longitudinal motion. We've developed our lateral motion. We can get a transfer function for our input to course angle. So we did aileron to our course angle and our rudder to our side slip. And now we're going to look at our longitudinal motion. For our longitudinal motion, we're going to be, again, I spelled plane. We're going to be looking at our pitch rate, altitude, and airspeed. And the inputs that we'll consider are our elevator and our throttle. And we're going to use those things to control our altitude and our airspeed. So let's jump into that. Again, if we're looking at our equations of motion, slightly corrected from what were in the book. So we're looking at Q and theta dot, Q dot and theta dot, and H dot. Those will be the big ones that come in from these equations of motion for helping us in the longitude. Oh, I put lateral there. That should have been longitudinal. Okay. So first we're going to be looking at pitch. So we have our equation for pitch given above. And what we can do is we can start manipulating it just a little bit. Very similar to how we did before. We're going to just do a plus Q minus Q, right? So that way we end up getting this cosine of phi minus 1. That is almost equal to 0, right? Especially when our phi is really small. And minus r sine of phi. And this is going to be also equal to 0 for small values of phi. So that's where we get that theta dot is nearly equal to Q. And then we'll just chalk in a disturbance there. Again, we want to get to the input where if we look at the input that we care about, right, we're going to be looking at our elevator. Sorry, I was trying to find that. There we go. Here's our elevator. It's going to obviously affect Q. And then Q comes in and affects theta. So we just take the second derivative of Q. And to do that, we'll end up getting Q dot, or using Q dot, right, for this component right here. And that's where we get everything right there. So that's all just Q dot. Maybe I should have pointed Q dot instead of Q. And then we have the time derivative of our disturbance. Okay, so we're going to do a couple of things while we're rearranging it. We have Q in there. We'll say that that's approximately equal to theta minus our d theta 1, just from this relationship right here. So we have a relationship between Q and theta dot. Sorry. And then if we're assuming no wind, so we assume no wind and we convert alpha to theta minus gamma. And this we get in our no wind condition. We know that gamma is equal to gamma sub A, which is always equal to, and I should put no wind, so this is approximately equal to, this is always equal to theta minus alpha. Sorry, that was hard. Okay, so we then get this relationship. We can replace alpha with theta minus gamma. Okay, so we'll collect terms that we care about. We care about, because we're worrying about theta, we care about theta dot, and we care about theta, and we care about our input, right? Everything else that's in this bracket, we chalk up to a disturbance. Excellent. So then we have some constant times theta dot, a constant times theta, constant times our elevator input, and then we have our disturbance. So now we can, just as before, start to write our transfer function model. Okay. So we have this nice relationship. What we can do is if we take the derivative of this, that corresponds to adding this s. So we add a derivative. And when we add the derivative, our derivative of theta is nearly equal to q. And we do this because then we can utilize q when we're doing our feedback control. And then we're going to then integrate. So we took a derivative and then we integrate and we get theta out of it. So this is fantastic because now we have a way to get to theta. So we take our elevator, we're able to define a relationship between elevator and theta, and in the middle we have q. And we'll utilize that formulation to help us develop a control law. Okay. So now what we really want to control is not necessarily theta, but we want to control our pitch. Or we want to control our altitude. Theta is our pitch. Okay, and we use similar assumptions, right? So assuming constant airspeed, we have VA dot is equal to 0, so we don't have to worry about any change in our airspeed. This also, the developments down here also assume that we're close to a straight and level flight. So we're not taking into account much of our pitch at all. So in this case, our V would be nearly equal to W, would be equal to 0. Our U is then going to be equal to VA. Our roll angle is, since we're straight and level, is going to be nearly equal to 0, and theta is going to be small. So if we do that, then we can write that our height, our time derivative of height, is equal to VA times theta, right? All we did here to get from line 1 to 2, where we just add VA times theta and we subtract VA times theta, right, which is equal to 0, so we can always add in 0. So that's where we get this VA theta. And then if under these conditions that I've written up over here, each one of these terms is going to be close to being equal to 0. So U is nearly equal to VA is what we said. Sine of theta is nearly equal to theta. So we get this VA theta minus a VA theta. So it's really small. V is nearly equal to 0. And sine of phi is nearly equal to 0, or phi, whichever you prefer. Cosine is equal to 1, right? So this ends up resulting in 0. This guy is nearly equal to 0 again. 1, 1. So this guy is approximately equal to 0. So that's where we get this relationship. So we can chuck these all up to just one big disturbance. Or, I guess, one small disturbance. If it was a big disturbance, it'd be problematic. And then we get our transfer function from theta to our height. This is that simple relationship. But the cool part now is we have our elevator and we get up to our height. Okay, so now we'll jump in and start to look at our airspeed. And this is the one that starts to give us a little bit of a headache. Everything else worked out quite nicely in just identifying terms that were small. Now we're going to actually have to use our trim trajectory a little bit more. Okay. We have a relationship where both the pitch angle and the throttle will strongly affect airspeed. And we saw that in our videos. If we're going, if we wanted to go really slow, we needed to actually have a decent pitch, basically give us some more drag as we're going through. So So we're going to derive this relationship. So if there's no wind, then what we're going to do is no wind. Again, VA is just going to be equal to the magnitude of our velocity, right? So we get this first condition. And another condition related to this, we saw in chapter 2, we could write UVW. If there's no wind, this is just equal to UR, VR, WR, which these guys were equal to, VA times cosine alpha, cosine beta. We have sine beta and sine alpha, cosine beta. So we have this relationship if there's no wind. Now we need a value for VA dot. We've never taken the time derivative of VA. So let's take a look at that. If we say that VA is equal to, I'm just going to say that's equal to the square root of P, where P is just some variable that we're using right now for differentiation. So we'll have VA dot. We'll just use our standard calculus techniques. It's going to be the derivative with respect to P of the square root of P times P dot, right? Which, if P is equal to U squared plus V squared plus W squared, P dot would just be equal to 2U U dot plus 2V V dot plus 2W W dot, which is excellent. So now this guy is going to be equal to, well, if we take the derivative of the square root of P, we're going to get 1/2 times divided by the square root of, not 1/2, just 1/2 times the square root of P. And then we bring in our P dot as times 2. We have our U dot plus V dot plus W dot. Okay, so that cancels out. This guy is equal to, square root of P is just equal to VA. So VA dot then is equal to U dot plus V dot plus W dot all over VA. Okay. Which is where we then can start to work with this equation. So now this is U dot. Remember that U sub R, U, we could replace U here with a VA times cosine alpha cosine beta. But if we're taking the time derivative, that's going to also be divided by VA. So we get rid of the VA on the right-hand side. So these guys end up coming in here, right? The sine beta and the sine alpha cosine beta. Okay, and we take these two conditions and we check up the other ones to disturbances again. So we're saying that if beta is small, this guy is nearly 1, this guy is nearly 1, so, and this guy is nearly 0. So these are going to be small perturbations, and so it's just going to be, the disturbance is going to be small. Okay. Now we substitute in the dynamics, right? We have U dot and W dot in there. And we're going to use basically the same tricks as we did before. We end up grouping like terms, but we end up with this equation, which it didn't linearize, right? All the previous ones, we were stuck with some nice equations right here. We still have that, we have a squared term here, and we have this guy, our thrust from our propeller, which is still quite nonlinear. So we got to come in here and deal with that. So since it's nonlinear in VA, what we're going to do is we're going to linearize about, instead of about 0, we're actually going to linearize about our trim trajectory, right? So these are going to be the new variables of our function. And if you recall our Taylor expansion, we can get we're going to get a first order approximation. And we'll do more on this with LQR. So we're not going to go into the details right now of reviewing Taylor again. But basically, we're going to take these, we'll take our nonlinear terms, and we'll use the linearization to pop up to just get the first order approximation for these functions. Okay, and the one thing to note here is that, or a couple things to note. Now, once I linearize, since I'm plugging in the nominal, so we plug in here, we have the plug in the nominal. This is a constant. Okay, so we have a constant there. The other thing to note is that we have our theta bar, we have our delta t bar, and our VA bar. These things, and everything else is constant, but these things are variables, and be careful, that's not theta, delta t, and VA, right? These are defined, delta t and VA. Let's see what those, there we go. They're defined as the difference from the nominal. So they're going to be small, but that doesn't mean that theta has to be small, or it doesn't mean that VA certainly is not small, nor is the throttle. Okay, so this transfer function is different from the others. So it's different in that it's defined in terms of the nominal of deviation from the nominal. Okay. But other than that, it's just another transfer function. And so now we have some constants, and we have this disturbance, which has everything else in it. Okay. So we then have these constants. All of the other disturbances we're assuming small, and we can then get our transfer function out of it. Okay, and again, this is very similar to what we've done before, since everything is defined in terms of just these constants multiplying by the states we care about. Now we have our delta t bar as an input, and our VA as our output, right? And we're just arranging terms just like we did before. So we have our throttle, and that throttle, we take in our theta bar and our throttle bar, and that gives us a transfer function for our airspeed, which is fantastic. Okay, so in summary, we've defined lateral and longitudinal transfer functions, right? And so here's the diagrams for it. Our inputs, again, we have our aileron ends up going through P through phi to get to our course angle. So to control our course angle, we're going to use our aileron. Our rudder is going to be used to get to our side slip. So to try to keep our side slip 0, we're going to use our rudder. Then we have our elevator, and our elevator will affect theta, which will then affect our altitude. And we have our thrust and theta. So we have theta coming down here, basically. That's a theta bar, right? And these two things are going to combine to affect our airspeed. So now we have a nice relationship between our inputs and the desired outputs that we want to control.